Okay, so question 1, the answer is cobalt. And the reason is because it passes through both the food and the packaging. Now you could have said technetium as well, because that is also true for technetium, but the difference being for the third mark that the half-life of the cobalt is long, so it's 5.3 years, is much longer. And when you're irradiating food, you're doing it in a production line, and so you just pass the food underneath the source of radiation. So you want to keep irradiating various items of food for many years. Therefore, you'd have to stop the process and replace things every so often. So the half-life is long, and that's what makes it the most suitable, because it doesn't need to be replaced very frequently. A lot of people said something along the lines of, "Oh, it's a short half-life, so it won't stay in the food, and it won't harm people who eat it." Well, you're not putting the radioactive isotope in the food. You're exposing the food to the radiation that comes from the isotope. So it's like having the isotope in one position and the food passing underneath it, and the food gets exposed to the radiation, rather than it having the radioactive isotopes in the food. 1B, very quickly. One reason why some people might be concerned about the safety of eating irradiated food, well, people link the use of radiation to cancer, or they think that the food becomes radioactive when in fact it doesn't. So they think it might be harmful to them, but it's actually not. So it's this idea that they think something, i.e. the radiation, is harmful. Because they think that, like some people have written in question 1, they think that the radioactive isotopes are in the food, but they're not. 1B has nothing to do with radiation, really. You look at one keyword in the question. The keyword is independent, as part of the phrase of independent scientific committees. They are independent from government influence. So if you see the word independent and it's a 1-mark answer, it's always to avoid bias. Okay, why are scientists independent? It's because then that avoids bias. One B, part 3. Most people gave the right idea that no, it doesn't make a difference, because there's some of the vitamins are greater in irradiated food than in non-irradiated. And there's no distinct pattern to all the foods being affected negatively. So some foods have more vitamins than others. But hardly anyone quoted values. So for the final marks, you had to give some value. And you could have also said that the data only refers to cooked chicken. So does it apply to every other situation as well? That would be a 3rd mark as well. B, part 4. Well, by telling people whether it's been treated with radiation, it's just allowing choice. So people can choose not to have it if they wish, even though there's obviously no element of radiation being emitted by the food, but it gives people the element of choice. C, part 1. It said there were 2 parts of this question. There was the what is it part and the where. And people either did that or they did this bit. So they either did the what is it or they did the where, but not both. So the answer is that it's an electron from the nucleus. So 1 mark for saying 2 things. Make sure to do what the question tells you to do. And then 1C, lightsaber, 1C, part 2. So this is how I would solve this problem. You simply have to follow this. So a sample contains cesium-137 and has a count rate of 600 per minute. So we'll start with 600. how long would it take for the count rate from the sample to fall to 75 counts per minute? Well, it's talking about half-life. So what I'll do is I half this number and draw this loop in. So that becomes 300. It's not a 75 yet, so I carry on halving the number until I get to 75. There we go. I've halved it to get to 300. So just here, I've halved it once to get to 300, and I've halved it again to get to 150, and I've halved it again to get to 75. So now I know how many times I've halved the original number 600. Well, I've halved it here, here, and here. 3 times. And each of those times I've halved it, it's taken a certain amount of time. And the question tells you how long it takes to drop by half. Well, right at the top of the part C, it tells you that it takes 30 years for the half-life. So each of these loops is 30 years. So 30 years for the first one, 30 years for the second one, and 30 years for the third one. So I add them all together to work out how long it took in total, which is 90 years. And you absolutely must do the same thing every time here, that method, to work out how many half-lives it takes to go down to a certain number, to work out how many years it takes to drop down to a certain number. And there can actually be slightly different variations on that theme, but you use the same method, and we'll go over a few more in the lesson on Friday or next week, probably next week. Question 2b. The question is asking you in the last line, why did the experiment lead to a new model? So a new model replacing the plum pudding model. So why do you ever have a new model in science? Well, it's because the old model doesn't explain your observations. So you have to come up with a new model which allows an explanation of what you see. And when I say observations, I mean either data or evidence that's collected in an experiment. So you have to come up with a new model which does, and that's why they replaced one model, the plum pudding model, with a new model of the atom. So that's all that question is asking you for 1 mark. Okay, 4b. So in 4b, we have to understand a few things about how types of radiation behave in a magnetic field. And we have 2 fields that can affect it. A magnet can affect, or 2 magnets can affect the direction which particles travel of radiation, and the electric field can affect how the particles of radiation travel. So alpha and beta have their directions changed. But in the question, the count before and the count afterwards are pretty much the same. Remember, radioactive decay is random, so this number will not be exactly the same as that number, but they are very similar. So we can essentially say that it's the same count rate. So if there was a source, or if it was a source which emitted alpha radiation, then beforehand the alpha radiation would have gone straight through and been included in that count, and afterwards it would have gone and been deflected, as we can see here. It would no longer reach a detector. So beforehand the alpha particles would go straight through and be included in that count, and afterwards they wouldn't hit it. So if that was the case, if there were alpha particles, we would see that this number would be significantly higher than the number afterwards. But it's not, it's very similar. So that means, that tells us that no particles are being deflected that way or this way. And so all the particles that went straight through the first time are the same as the particles that went straight through the second time. So that leaves only gamma as the only possible explanation. So the source is a gamma radiation source. Finally, 4D, it asks why the half-life is not long enough. Well, it's not enough time to take measurements, and that is because the radiation level after the amount of time that would have passed, the radiation level will become insignificant. So there's not enough time to make observations before the level of radiation becomes insignificant. Right, those are those series of questions. Practice more on those next week. Make sure you annotate your homeworks. And James Ashman, I've got your sheet. I found it. If you want to come and collect it off me tomorrow morning, that'd be great. Thank you.